Now we can apply all those ideas and all the information we've been gathering to establish the link budget for the phone. We're going to study the uplink and later on the downlink in different situations. This is just a simple sketch to help you not to get lost in the numbers you are going to see afterwards. And this is how we proceed when we establish a radio link in any wireless system. We have here one axis that is power axis. Could be absolute power or it could be dBms, whatever you want to use. So this is just the power level we are considering. And we start with the transmitter. On the transmitter side, the first parameter that is important is the power that we are transmitting. So this is just our power level and transmission. If we have antennas, we normally have, and they have some gain, that means that this power level will be increased by the gain. In fact, we move from the transmitted power to the equivalent isotropic radiated power or some other form. So really here we have a gain, so this increases our power. But if between the transmitter and the antenna we have cables, we have connectors, we have things, then we may have a loss. So the transmitter power is increased by the gains and is decreased by the losses on the transmitter side. So at the end, we start with the transmitted power, we apply with the gains and the losses, and we end in this blue line, that is the level of power that is being transmitted. Okay? Now, on the receiver side, we start with the noise. This is going to set our threshold. So for this system, with the parameters it has, we establish the noise power. And this is just here, Pn, this is our starting point. Okay? Now, we have to add the noise plus the interference. We have also to contemplate interference, which in cell phones is important. So now we have here noise plus interference, and we just go up a little bit in power. We have more power there. And we have arrived to this point here. But then the system requires a minimum signal to noise plus interference to work correctly. That means that we have to add again a certain threshold. So now we are at this level. And this is the minimum signal we may require. But you have seen that in those cell phones we have processing gains. So you are capable of, in some way, bringing the signal from the noise up. This happens not only in cell phones, for instance, this happens also with GPS signals. They are very noise, but since we know the code, the satellite is transmitting, then through correlation we can bring the signal up from the floor, the noise floor. So this is the minimum signal power, but all the processing gains bring us down. And the margins and the losses we have to apply, they bring us here. So this means the receiver power. You can think in this process in the following way. Assume you are in a room and you have the ceiling and you have the floor. You can increase the clearance in two ways. One is just pulling up the ceiling. And this is done by the gains, but the losses will bring it back. But you could also increase the clearance if you do another different thing. You just lower the floor. And this is what the gains do, and the losses will bring it up again. So at the end, you have those two power levels, the transmitting power and the receiving power. And this range, those two values set the maximum allowed path loss. If your path loss is less than this value, you are in good business, because now you are receiving a signal that is above this level. Okay? But if you are below, then you are in trouble, and you have to start improving your system. So remember, the main parameters here is the transmitter power, all the gains and losses. Here, the noise, once again, interference, the signal-to-noise ratio, and all the gains. This will define the receiver sensitivity, the minimum signal you need to process, and this is affected by the gains and the margins. And with this, now you could also find, once you have the path loss, you can have also the range. You can see how far away from the phone or the base station you can be and still be within this range, this allowed range. Okay, so remember this idea, remember this schema, and we are going to apply this to the uplink. And I'm considering here two different situations. First one is you are in a car on a highway driving at 120 kilometers per hour. And you are going to make a phone call at 12.2 kilobits. This is the first one. The second one is you are walking in the city and you just want to connect to send some data at 64 kilobits per second. You are outdoors, walking, medium-sized city. Right? So let's assume that the base station that is controlling your mobile phone, in both cases, has set your level at 21 dBms. Could be quite different depending on the situation, but let's take this number. Now, the antenna on your phone has no gain. It's inside the circuits, it's in the middle, it's your hand, your head, so there's no gain. Also, it's close to your head, so you have to account for a 3 dB loss here. In the data connection, I don't take any loss. You are inside the car, so you have to add also the in-car loss. And let's take a value of 8 dBs. That means that taking all those things into account, for the car case, your equivalent isotropically radiated power is only 10 dBms, provided you were transmitting, radiating this power. But in this case, it's just the 21 dBm because we have no gain, no losses. So this is just a good case. Now, those data rates are spread on the 3.84 megahertz. In fact, the channel is 5 megahertz, but only we are occupying 3.85. Oh, this is the value. And with this bandwidth, the first thing we can find is the thermal noise power density, which is K times T naught. And this gives you minus 174 dBms per hertz. Now, we take on the base station a receiver noise figure. This is now for the base station. Before it was for the mobile phone. And the noise figure of the base station is 5 dBs. So the total noise power, assuming that the antenna, what it's seeing is just the noise of your body, of the earth, which is roughly the reference temperature T naught, will be the sum of this plus the noise added by the receiver amplifier, and this is in fact, when you sum this, you directly multiply by the noise factor, or if in the best in dBs you add the noise figure. So this is the total noise power. Now we have to add the interference. And to add interference, we need to know the load factor. And the maximum load factor here, let's assume is 0.5. It's 50%. That means that we have the same amount of power as we had noise before. Or if you want, we add 3 dBs to this noise. So the total noise plus interference power is minus 100 dBms for this case. And in this case, it's the same. We are dealing with the same parameters. Nothing has changed here. In the transmitter side, yes, but nothing on the receiver side. So now we can continue. And now we start to add on reception the gains, margins, and all the losses that could be implied. So our service bit rate is 12 kilobits and 64 for data. The chip rate is 384. This is the spreading of the code sequence. The processing gain for this ratio is 25 dBs and 17.8 for this one. The required signal-to-noise ratio is 5 dBs for speech, 2 dBs for data. So now we have before the noise plus interference, we subtract the processing gain, and we add the required signal-to-noise ratio. And this will give us the receiver sensitivity, minus 120, which is more or less the order of magnitude that you should remember. Now we go to the base station antenna. It has a gain. It's a sector antenna that has 18 dB gain. But it has a cable that introduces a loss of 3 dBs. And then we have to incorporate the margins. On one side, we have the fast fading margin for the data connection. No margin, we are taking no margin for the car case. For the slow fading case, we take 7 dBs. We have to contemplate. On the highway, you probably are connected just to a single base station, but in the city, maybe you are connected to more than one. So here we have a 4 dB gain. That means that at the end, the maximum allowed path loss in the uplink, when you take into account all those parameters, is 138 dBs for the speeds, 145 for data. And this is the maximum path loss you can handle in this problem. Now we can apply this for studying the coverage. And here we have the frequency, 1900 megahertz. We have the base station height, 30 meters. We have the mobile antenna, 1.5 meters. And then we apply the Cox-Hattan model for the highway, and it gives us this number in terms of the distance in kilometers. Look, this is larger than 20. That means that the signal decays at a faster rate than it does in free space because of the environment. And for the urban case, look at here, we have just this number which is much larger than this. So this, in this case, makes things different to us. And now we apply this model to the path loss we had before. And with this model, when we use those numbers, then at the end we have those cell ranges. That means that when you are driving, you could be connected with those parameters to a base station that is up to 6.5 kilometers from you. While you are walking in the city, maybe you could connect to a base station that is 1.5 kilometers from you. So those are the basic parameters for the uplink. That's when you call from the mobile phone to the base station in those two different situations.